Okay, today we're covering Chapter 29, Sections 7 through 8. And these are the concept question exercises we'll cover today. So please go read the sections thoroughly and then practice with these problems, coming back to the video, pausing to do your own work. Okay, we're going to start with number 6. This is practicing with the magnetic force law. Okay, so we have a particle, a charged particle, a positive charged particle, that is traveling to the right in a magnetic field that everywhere is pointing into the page. So our magnetic field is given by the X, meaning it's going into the page. Okay. The question, what is the direction of the initial magnetic field or magnetic force by that field on this particle? Now, just as a reminder, we're talking about magnetic forces. It's magnetic forces by a magnetic field acting on a particle. This magnetic field is not from this particle. It's from something else, a solenoid or something else that we can't see. Okay. This is definitely creating its own magnetic field, and we could calculate that if we wanted to, but that's not the magnetic field we're talking about. So when we think about the magnetic force law and we see a QV cross B, the B is from something else. Okay. All right, so with that, what is the direction of the force on this particle? Just direction. Okay. Well, I made a handy-dandy right-hand rule thingamajiggy. Okay. This is 3 toothpicks that are actually they're barbecue skewers that I've painted green, blue, and red. Okay. Now these are going to match the vectors drawn in the text, with green being a velocity, a blue being a magnetic field, and red being the force. Okay. All right, so we're going to try and use this to help understand this problem. The main idea is that our force on a particle is QB cross B. And the rule of the right-hand rule is that the finger of your hand points in the direction of the first vector, which is velocity, and then the next finger is the magnetic field, and the thumb would be this resulting. Okay, so here I've drawn it to make things a little bit easier. This is the first vector. Okay, so it'd be like this. If I was going to, so there it would be like this if I'm matching my hand. Okay, velocity, magnetic field, force. Velocity, magnetic field, and force. Okay, so using like this, my velocity is to the right. Okay, so I've got it pointing to the right. The magnetic field is into the page, so in order to make that work, I have to tip this up like this, so the magnetic field is into the page, which means the force, the magnetic force on this particle by that field is pointing up the page. Okay, so we can write that down. Our force is up the page. Now note, this was a positive particle. Okay, so that's all good. Now in part B, we have a change in setup, but also I want to emphasize the change in particle too. So now we have a B field that everywhere is out of the page. Okay, and we have a negative charge that's traveling upward. Okay, use your hand, or if you want to, go make something like this to help out. All right, it's just a blob of hot glue connecting these things together. All right, so go. What is the direction of the force acting on this charged particle by that magnetic field? Okay, so to see that, I'm going to go to my green velocity vector. Okay, my blue magnetic field is pointing out at you, which means the force would be to the right if this was a positive charge. But since it's a negative charge, I just reverse that result. Okay, so again, the right-hand rule works for the positive charges, but if I have a negative sign there, I just flip whatever my final answer is. Okay, so since my right-hand rule said it's going to point to the right, then the force on this will be to the left. Isn't this nice? This is so much nicer than my hand. Okay, so now let's move on to number 7 and try and apply these same principles. Okay, so we have a positive charge moving to the right in an area where the magnetic field is everywhere pointing down the page. What is the direction of the magnetic force? Okay, right-hand rule. I need my green pointing to the right. Okay. My blue needs to point down. Okay. So I've got green pointing to the right. Here, let me just hold on to it like this. Green pointing to the right. Blue is pointing down the page, which means my force must be into the page. Okay, my force is into the page. So the force is into the X with the circle around it, or into. All right, part B, I have a negative charge moving upward in a magnetic field where everywhere it's upward. Okay, what is the direction of the force in this case? Well, if you're having a hard time using your right hand, or if you built one of these cool little thingamajiggers and you're having a hard time doing that, it's because the magnetic field's 0. These are parallel, they're not perpendicular, and cross products only care about perpendicularity. If they're parallel, the cross product gives you a 0. I mean, I could try that. I could say, here's my velocity vector pointing that way, but this blue one stays perpendicular. I can't make it. I can't make it parallel. Okay, and so this gives us a 0. F equals 0. If this was the case, this particle would just fly straight on through without any effect. Okay, let's switch this up again, practicing with a little bit the same idea, but with a little bit different order. In number 8, we've got a particle, positive charged particle, that's moving to the right, and instead of being told the magnetic field, we're told that the force it experiences from some external magnetic field is downward. So what is the direction of the magnetic field that caused that particle to feel a downward force? Use your right-hand rule. Okay, in this case, it is our blue that we don't know. Okay, so our green is to the right. We know our force, which is down, which means our magnetic field must be out. So B in this region of space must be out, or the dot in the middle of the circle. Okay. Okay, part B. We have a negative charge moving to the right, and we have a force that is into the page. Okay, this force is into the page. What is the direction of the magnetic field that caused that force? Okay, so our green stays this way, but our red needs to point into the page, which means our blue is pointing down the page. But this is a negative charge, which means we just reverse that result. So the B field is pointing up. So everywhere in this region, the B field is pointing up. Okay? Very good. Practice one more iteration with this. 9. We have a negative charge that's flying this way, and F is out of the page. What is the direction of the magnetic field that would cause that force? Okay, so we have our green velocity. And our force is out of the page. So it's like this. This force is out at you. which means our magnetic field is kind of down and to the left. But it's a negative charge, so we just flip that. So it's going to be opposite down to the left, which is up and to the right. So the magnetic field everywhere in this space is up and to the right. I didn't actually have to draw it like that. I could have drawn it over here. This is just representing the field everywhere here. Okay? And then part B, we've got a positive charge. It's traveling down and to the right. What is it? Oh, and the force. Oh, I apologize. That's the force, not the velocity. A force is acting on it down and to the right, and the velocity is into the page. Okay. The velocity is into the page. The force is down and to the right. To the left, sorry, down and to the left. What is the direction of the magnetic field that would cause that force on that charged particle? Okay, so let's get our green pointing into the page. All right, and our red points down and to the right, which means our blue is down and to, sorry, head is down and to the left, which means our blue is down and to the right. And it's a charged particle, so that is indeed what it is. Or sorry, it's a positive charged particle, so that's indeed what it is. Okay, so we've just pretty much really hashed out this law, but mostly focused on the right-hand rule and how it works to get that. Okay, instead of using my hand, I used a right triangle with directionality imposed by the color. So it goes this way, from green to blue to red, green to blue to red. I always follow it that way. Okay, let's go jump to some of these exercises, see what we can do. We've got number 33. Okay, so number 33, this is a fun one. We've got a wire that has a mass and a current. Okay, current flowing this way. And it's in a region of space, this region of space where the magnetic field exists. Okay. Now we don't know the direction of the magnetic field, but we want to find out how big and in what direction that magnetic field is in order to levitate this wire. Okay. So to think about that, if this is a side view, then our gravitational force would be down. Okay, gravitational force would be down, which in order to levitate it means our magnetic force must be up. Okay. And looking at that as a free body diagram, those must be equal because it's just levitating. It's sitting there in midair. Okay. So in order for the magnetic force to be up and the currents flowing this way, we have our magnetic force law, but written for currents is F equals I dl, or I guess we could just use the full length. The total force equals the full length I dl cross B, or IL cross B. Sorry, that's looking a little ugly. I L cross B, where L is the length of the wire being affected by the magnetic field. So in this case, what is that? Is that this total length of the wire? Or is it the length of the wire that's actually within the magnetic field? And the answer is, it's the length of the wire within the magnetic field. If there's no magnetic field out here, then there's no magnetic force on this piece of wire. So we just care about the force acting on this length of the wire. Okay, so with that, how do we find the direction of the magnetic field that would cause that force on that current? Let's use our right-hand rule here. This time, our green is the direction of the current, which is the same as the velocity for a charged particle. Okay, so current's flowing to the left. I want the force to be that way, which means the magnetic field needs to be out of the page. Okay, the magnetic field needs to be out of the page. So B is out. Okay. So again, current's flowing to the left. The force on this wire is vertically upward, which we'll use y hat to mean upward, away from gravity. And that means the magnetic field needs to be pointing out of the page. All right, now that we've got that direction, we can just focus on magnitudes. Okay, so the size of this force, we have this FB pointing up, this FG down, and we know F net is 0, so we have our upward force of FB, which is ILB. Okay, they're perpendicular, so we get just the products. The sine of 90 equals 0, or equals 1. And then subtract mg, that's the downward force of gravity, equals may, but it's just levitating, so it's 0. Now we can solve for that b. B equals mg divided by il. If you plug in your numbers that are given in the problem, again noting that the length used is the length of the magnetic field, or the length of the wire within the magnetic field, because that's what's receiving or feeling a force. So you'll get 0.13 Tesla. That's actually a sizable magnetic field to be able to levitate that very small mass wire. Okay, so we're going to put a vector sign here and say that that is out. That would be our answer. Okay, so this is a good one because we're applying a new force, but applying it to a standard fundamental system or method using Newton's second law and equating forces to find the answer. Okay, let's look at 36 now. This is a good one to really be careful to focus on what's causing the field and what's feeling the force from the field. Okay, what's causing the magnetic field and what's feeling the force due to that magnetic field. Okay, so we have 3 wires. They all have 10 amps of current flowing through them, and they're all of the same length. Okay. The middle wire has a current flowing the opposite way as the outer 2 wires. And the spacing between the wires is the same. All right? Okay, so our question is, what is the magnetic force, magnitude and direction, on each of these 3 wires from the other 2? So what's the force on this one from these 2? What's the force on this one from these 2? And what's the force on this one from these 2? Okay, let's start with the middle one. What is the force on this wire due to the magnetic field created here by these 2 wires? Okay, notice how I said that. It's very important to keep it clear what the process is. These wires, so this wire creates a magnetic field all around it. And we have a relationship to figure out what that field looks like and how big it is. So it's creating a field here. All right. This one's doing the same. This one's creating a field here. The net field will contribute to the force acting on this wire. Now this wire is also creating a field, but that's not the field we care about. A thing cannot act on itself. So though this creates a magnetic field, we don't include that field in the calculation of the force on this wire. Okay, so in doing so, let's find the magnetic field at the location of this wire due to the other 2 wires. Starting with this one, the current's flowing that way. The position of this wire where we're measuring the field from this wire is below it, so our R vector is down. Okay, and if I use my right-hand rule with IL cross R hat to get the direction. All right, that means that let's pull out our thing. In this case, we'll use green to be the current, as it was before. Okay, blue will be the R hat, and red becomes the magnetic field. Now I can't keep blue to be magnetic field in this case because the magnetic field is the result of our equation for magnetic field. B equals mu naught over 4 pi I dl cross R hat over R squared. Okay. B is now the result of L cross R hat or I cross R hat. Okay, so over here, F is the result of V cross B. So they have very specific positions in the cross product. And the right-hand rule follows those specific positions. So V or I are in the same position in these cases. So I can allow that to be the green on my little doodad. But now the second thing is R. And so I'm using blue to be R, which means red has to be the magnetic field. So remember, this is a cool little doodad, but just like everything else, green's got to mean whatever you tell it to mean. Okay? And it's got to follow those rules. Okay, so we have current, R, and B, magnetic field. So our current is flowing to the right. Okay, our current's flowing to the right there. R is down the page. Okay. R is below that wire, which means the red, which indicates the magnetic field created by that wire at the location of the middle wire, is into the page. Okay, so the field here is into the page from this one. I'm going to call this B1. We'll label this 1, 2, and 3. Okay, so the field from B1 is into the page. So I'm going to make it a little bit clearer. B1 is into the page at the location of this wire. Okay, do the same reasoning to find the direction of the magnetic field from 3 at the location of this wire. Do the same ideas. Okay, first of all, our current's flowing to the right, just like this one was, but our R vector is now upwards. Okay, that's upward now. And so the magnetic field, you can guess, by reversal of one net value, is going to be now out of the page. So let's just try that. We have current flowing this way. Okay, blue is our R vector, points up, which means the magnetic field created by the third wire at the location of the second wire is out of the page. My red is pointing out. So B is out of the page from 3. Okay. So that's how we have calculated the magnetic field direction at the location of the second wire due to the other wires, the sources. All right, now that we've got that, what is it? Well, they're identical currents, identical distances. If this one's in and that one's out, then the B field there is 0. Okay. Those add together, they cancel each other out. There's no magnetic field there, which means the force on 2 is 0. There is no force on 2. Okay? All right. Now, that was laborious because it's got a lot of complicated parts with right-hand rules, recognizing what's acting on what. Okay? So now, let's go ahead and look at the force on wire 1 by wire 2 and 3. So what's the force on this wire due to these two? Okay, let's redraw it because it's kind of messy. That current's flowing that way. Okay, so this is 3, 2, and 1. So first, find the direction of the magnetic field here due to wire 2, and then again, the field here due to wire 3. Find those. Okay, now R2 is up, and R3 is also up. Okay, so our current's flowing this way, in R3, in current in wire 3, R3 is pointing up, okay, which means that the field here, due to this wire, is out of the page. So we get a dot, and that's B3. Okay. Now, in the case of wire 2, current's flowing to the left. R is still out of the page, or upward, which means the B field from I2 is into the page. So the B field at location 1 is into the page from B2 and out of the page from B3. Now, do they cancel like down here? The answer is no, not this time, because there are different distances. The currents are the same, but they're acting over different distances, and we know for a long straight wire that the magnetic field decreases with distance. Okay, so we need to now find B net at 1. All right. Okay, let's go ahead and just choose one of them to be, one direction to be positive, either in or out. Okay. This one is closer, and I know that magnetic fields get smaller with distance, so this is going to create a bigger field. So B2 is going to be bigger than B3. So I'm going to choose into the page to be positive. Okay. So by choosing into the page as positive, then I'm going to say that B2 is going to be B net is going to be B2 minus B3. And then what are those? Well, for a long straight wire, I can look that up on my study notes. I have mu naught I, and I'm going to put a 2 there right now, over 2 pi R2. Okay. The magnetic field is created from this current 2 at a distance R2 away from it. Then minus mu naught I3 over 2 pi R3. Okay. Now notice I'm using just magnitudes here because I've already taken into account the negative sign based on my what I did with the right-hand rule. All right. So with that, I can plug in what I know. I know the currents are the same, so I'll just call those I. I know this one's twice as far as this one. Okay, so I have mu naught I over 2 pi, I'll call that D, as I did over here in this picture, and then minus mu naught I over 2 pi 2D. Okay. So I have mu naught I over 2 pi D, and if I pull that 2 out as a half, I get 1 minus a half of the same quotient. So I get 1/2 mu naught I over 2 pi D, or just mu naught I over 4 pi D. Okay. So that's how big the field is. Now notice we spent all that time just finding the field there due to these other 2 wires because we had to add them up vectorially. All right, now we can get to the point of what is the force. Okay, well the force acting on a long straight wire is given by this equation, which we've already used. So now that we have the B field, and it is perpendicular to this current, it's a positive value, which we chose into the page as positive, that's perpendicular to I. So what is the magnitude of that force? Well, F is going to be I1, okay, then L1, then cross B, but that's 90 degrees, so I'll just say by B net at 1. Okay. So knowing that the I's are all the same, and I have the length, so I have I, and I guess I gave it a capital L over here for my labeled diagram, and then B we just found mu naught I over 4 pi D, and I can combine the I's and do some simplification, but that's basically it. So I found out how big it is, and if you do plug in your numbers, you're going to end up with 2.5 times 10 to the negative 4 newtons. Okay, 2.5 times 10 to the 4 newtons. Pretty small because these are magnetic fields are fairly small. But the question is this pulled towards them? Is it an attractive force, or is it pushed away from them? Okay. Well, we can use our right-hand rule thing to do that. This was an IL cross B, and we determined that B was dominant into the page. Okay. So our current's that way, and our B field, now again, we're using this rule, not, you have to keep these straight. We're not using this rule, we're using this rule. So the first thing is the current, the second thing is the magnetic field, the third thing is the force. So our current is thing being acted on, I1, pointing that way. The B field that's acting on it is our blue. It is into the page, which means the force on 1 by 2 and 3 is upward. So that's upward. Okay. So that was a nice, fairly complicated problem, but a good review of these processes. Again, keeping straight. First, you have to think about the field created by sources. And then once you have it, then you can think about the forces by that field on a test charge or current. Now we could ask, well, what is the force on this one by these two? But by symmetry, it's going to be the same thing, but in the other direction. It's going to be downward. Okay? So we can just argue by symmetry that that's the same answer. Okay, I'm going to hold this problem. It's a review problem. I'm going to hold that for a different video.